So good morning, everyone. Welcome to the Western Hemisphere Virtual Symplectic Seminar. We're very happy to have Susan Tolman today here from Illinois, who's going to give us a talk about Beyond Semitoric.
Yes, okay, well, thank you very much for inviting me. I'm very happy to be giving a talk here. And so I'll just say this is a joint work with Daniel Sepe. Okay, so I'm going to start off with a little introduction to integrable systems. Some of this I know will be reviewed to you guys, but anyway, it'll go pretty quick, the review part, hopefully. So an integrable system is a 2n dimensional symplectic manifold, M omega, and a function capital F from M to Rn. So it'll just be F1 through Fn. And I want to assume that Fi and Fj Poisson commute for all I and j, and that capital F is regular on a dense set. So these are all the standard. And so there's some important examples. So first of all, we can let M be the complex numbers and F be the imaginary part of Z. And so you can see the bottom, just looking at the standard symplectic structure, well, I guess maybe twice it, doesn't matter, on CK and just the imaginary part. Okay. And so, right, so you can have, we have that. And we have M equals C, and F can be the norm of Z squared. And so the first one, of course, is just inducing translation. The second one is just inducing rotation. You could let M equals C and F of Z equals the imaginary part of Z squared. This is a hyperbolic action. It's not a circular action. It's a little bit trickier. And we can let M be C, we call that, and we have M equals C squared, and F of xy, the first component could be the norm of x squared minus the norm of y squared, and the second component could be the imaginary part of xy. And that is called focus. And we can also take any product of the first two examples. Of course, we can take any product of any of them, but in particular, I want to focus on the case we have any product of the first two examples and call that toric. And I think I mentioned this, but for the focus, the first action that we're going to get is going to be rotation. You're going to have weight 1 on the first copy of C and weight -1 on the second copy of C. So these are all important examples of integrable systems. And if you are familiar with the notion of non-degenerate integrable systems, these are sort of the important examples of these are all important examples of non-degenerate integrable systems. I'm not sure if everyone's familiar with that terminology, so I won't use it unless I need to. So I want to start out by saying, what is a semitoric system? So just to start, what's a toric system? So when you have an integrable system, of course, it's going to generate an Rn action. So, and define the vector field. So you'll have n commuting vector fields, Ci, and d of Fi is minus, just take the 2 form omega and feed it the vector fields Ci. So this is going to define the Ci uniquely, and the fact that the Fi Poisson commute tells you that this gives you an Rn action. And we're going to say that it is toric if this generates an S1 to the n action. So the note, in this case, every point has toric type. And when I say something has a type, I mean 2 points with isomorphic neighborhoods have the same type. So in particular, when you say every point has toric type, it means that it's isomorphic to some product of these first two examples. The neighborhood of it is isomorphic to that. But we won't mostly be talking about toric. We'll mostly be talking about generalizations of toric. We'd like things to behave as if they were toric, even if they're not, or at least have a lot of the power that we get for toric systems. So a 4-dimensional integrable system, M omega F, and I'm going to write the first component of F here is phi, and the second one is G. And we're going to say this is semitoric if phi generates a circle action. So you need your first component to close up, not just be an R action, but be an S1. And I need every point to either have toric type or have focus-focus type. So it's either local neighborhood is isomorphic to the product of the first two models, or you have a neighborhood which is isomorphic to the focus-focus, which is the fourth example. Oops, sorry. Okay, so this is, if you're familiar with semitoric, this is not exactly the usual definition given. However, this agrees with the usual definition. As usually a sort of more of an infinitesimal condition, the way it's defined, but there's a number of work which gives you local number forms for that. So Eliasson and then Bunak, Washu, and Chaperon, and Miranda and Zhang have all done work on the local number forms. And using that, you can say that for just the sort of the normal definition of non-degenerate tells you that it must be some product of these first four cases. And then the fact that the definition of semitoric rules out the hyperbolic case. So if you're familiar with the normal definition, this is the same. The only difference is I'm not insisting on compact. I'll add compact when I need it, which usually I will add compact. But anyway, I'm not assuming it's part of the definition. Okay. Semitoric systems, there's a lot of results on semitoric systems, and I'm not going to give you a complete list because it's quite extensive and a little bit aside from what I'm doing today. But the first real theorem we have here is that if you have a semitoric integrable system and it's compact, then all the fibers are connected. And having the fibers be connected is a really important thing because it really gives you the first step on your classification. And there's a lot of further results. And like I say, I'm not going to be comprehensive, but there really is a complete classification that's very satisfying by Palaio and Bunak, and then Palmer did some, and then Palaio and Tang did some more. It's a really nice classification. There's minimal models. So you can say in terms of being blowups of some other example, and that was by Kane, Palmer, and Palaio. And there's also been a fair amount of progress on quantizing these. So that was Laflaq, Palaio, and Bunak are the most important names there. But like I said, I won't go into detail, but there's a lot of things that are known about them. So this gives us the pros, is the semitoric systems are well understood. I said a complete classification is great. And there are many interesting examples. But the cons are we want more examples. This really doesn't give us all the examples we want. We want to generalize the notion of semitoric so that we can get more examples. Okay, this is probably a good place to stop. Are there any questions on semitoric systems? Okay, because I'm sort of going to go on now to, okay. So I want to talk about, what I want to talk about now is sort of why are there not enough examples and what would we want to see if we had more examples. So let's start off with sort of a toric example. So let M be S2 cross S2 with the product symplectic form. And S1 can act by rotating the first sphere. So if you do this, there are two fixed spheres. And the moment map is the height of the first sphere. And so the moment map will be constant on the two fixed spheres. So here we have a picture. That's what this picture is supposed to indicate, is we have the two fixed spheres and the moment map is taking them to different values of R. And the claim is that M is secretly toric. Okay, it's not a very well-kept secret. I think everybody knows that S2 cross S2 is toric, but the point of view is we're starting with a manifold with a circle action on it, And we want to know, can I extend this to a larger action? Can I extend this to a toric action? Can I find another function so that this is toric? And the answer in this case is, of course, yes. I'm just going to take the height of the second sphere, and then I will have a toric system. Okay, great. So that's the simplest example. However, we might want to make this, we want to go beyond this example. And so what we're going to do is we're going to let m hat be the blow up of m at 3 points in one fixed sphere. And the example that I'm taking is I'm blowing up in the top sphere. And so what that's going to do is it's going to make the top fixed sphere smaller. And it's going to add 3 fixed points, P1, P2, and P3. Both the weights, all 3 points, I'm sorry, will have weights +1 and -1. It's pretty easy to check. You just go through it. And you can blow up, of course, by different amounts, but I want to do it so that each blow up is by the same amount, all 3 blowups. And then I'm going to get that my moment image of P1, P2, and P3 is the same value in R. So again, here you have my picture, and you can see the 2 fixed spheres, and the top sphere is a little smaller than the bottom sphere, but the moment map is constant on the spheres, and it sends all 3 fixed points to some point in the middle. So the first claim is that m hat is not toric, and that's due to Karchan. So she gave actually necessary and sufficient conditions for circle actions on 4 manifolds to extend to toric actions. So in my case, being secretly toric, she proved that it does not extend. On the other hand, it does admit a function to R that makes it semi-toric. So I can extend this map to R to a map to R2 so that it's a semitoric system. And that was by Halak, Sabatini, and Sepe. And so I will actually prove these. These theorems are due to them, but I will give a proof of those. Sort of ties into our proof. So I won't say too much about why they're true now. But I do want you to note that there's 3 fixed points all mapping to the same point in the interior. That's kind of the key. So that one was toric, but not semi-toric. And now we're going to give an example which is not even semi-toric.
Sorry, Sue, can I ask you a question?
Yeah, absolutely.
Can you say where the 3 fixed points come from in the previous example?
Yes. Yes. Okay. So I often look at my iPad. I'm not on my iPad now. I can switch to that if need be. But so the idea is, imagine this as a square, right? And if I chop off a corner of the square, I'm going to get 2 additional vertices. One which will still be at the top of the square and one of which is not. Does this make sense?
Yeah, that makes sense.
Okay. And so the one which is on the top, actually, I'm gonna boldly go and just switch to my iPad because I can tell I'm waving my fingers too much. So just give me a second. I'm sorry. This is let me go to, I need blank paper. There we go. Okay, right. So here we can see this very easily. So this is S2 across S2 when I think of it as a toric variety, right? I get a square. Now I blow up, which I can think of as chopping off a corner. And then if I look at this, is going to be the maximum, which I see as a little bit smaller. And this is the minimum, which has not changed at all. But now I get a new fixed point. And if I restrict to the S1 action, I've added a fixed point. And you can check that the weight for the circle action is going to be plus and minus 1. So now as a toric variety, I could chop off 2 corners. and get 2 fixed points. Now, I can't draw so well chopping off the third corner on the top because there is no third corner on the top and I have to blow them up in the same. And that's sort of my point. It's not torque anymore, right? So you don't expect my picture to be as nice, but I can blow up any number of points. It's just I don't have the torque picture so much.
Okay, thanks. That makes
sense. Question? Okay. So let me go back to my. Okay, great. So that's a good question because it's good to be able to see that. And this business about not having like another point to blow up is basically the proof that it's not torque, but I'll say a little bit more detail. It's sort of a, so now what do we do? So now we have this picture with 3 fixed points, P1, P2, and P3. Sorry. And now I'm going to blow up those fixed points. So if I blow up those fixed points, you can just sort of, again, you can think of this as chopping off. If you're happy with the toric picture, you can actually just chop it off and you can see what you get is that your point is going to become a 2-sphere. And your 2 spheres will have stabilizer. Each 2-sphere is going to be a 2-sphere, which is stabilized by Z2, and which has, of course, a fixed point on the top and the bottom. So now we're going to have 2 fixed spheres, 6 fixed points, and 3 spheres with stabilizer Z2. And if you look at the points, the 3 points on the bottom are going to have weights -1 and +2, and the points on the top are going to have weights -2 and +1. It's because of the spheres that are fixed by Z2. But in any case, our weights are not +-1 anymore. But if the blowups are equal, which is what I want to do, then these 3 spheres have the same moment image. So I have 3 fixed points that map to the same thing on top, 3 fixed points that map to the same image on the bottom, and then 3 spheres which also map to the same point. And so the claim is, unlike the previous case, this manifold is not even semitoric. And this is by Holub, Sabatini, Sepe, and Symington. So this does not fit within the category of semitoric. And this is sort of one of the reasons to feel like there's not enough examples. We'd really like to be able to understand this example and fit it within the world of cases that we are happy with. So I think this is another good place to stop. Are there any questions about these 3 examples, which sort of are the motivating examples for this talk? Okay, great. So now we're going to get into, I've talked about semitoric, I've talked about what examples can you construct with semitoric and what examples can you not construct. And now I'm going to get into sort of what we've done. How do we deal with this? So I want to take a step back and talk about complexity 1 space. So what is a complexity 1 space? So a complexity 1 space is a 2n dimensional symplectic manifold M omega. And an effective torus action, so it should be an S1 to the n-1 dimensional torus with moment map. Of course, we're going to have moment map 5 from M to Rn-1 now. So this is like the toric case, but my action is just my torus is 1-dimensional smaller. So here's sort of an example is let's identify some subgroup H of T with the subgroup of SU to the H+1, where little h is the dimension of H. Well, this gives us this gives us a linear H action on CH+1, just because SU to the H+1 acts naturally. And let's call its moment map phi sub H. So this is the map from CH+1 to H star. So we're going to define what we call a local model. And it's just the product of the torus T and the annihilator of the Lie algebra of H and CH plus 1. And we take that product and we divide by the H action, or H acts on T by multiplication and acts on CH plus 1 by the representation and does not act on H naught. And the claim is that there's an invariant symplectic form on Y so that the T action on Y is symplectic, and the moment map, it just sends the point T eta Z to eta plus the moment image of Z under the H moment map. So this is a pretty standard example. And I'm going to say that this model is tall if the reduced space, which is just phi inverse of 0 divided by T, contains more than one point. And if that is true, then all the non-empty reduced spaces will contain more than one point. That's easy to check. So the claim is, which of course many of you probably know very well, but for those who might not, is that every orbit in a complexity 1 space has a neighborhood isomorphic to a neighborhood of T00 in some local model Y. So essentially, if we want to understand them locally, all the information is contained in the local models. And we don't need, that's the only example we need if we want to understand things locally. Okay. So why is this important to us? Well, so if Y is tall, then there exists a vector in Z, an integral vector in ZH plus 1, so that every component is non-negative, such that we can define a defining polynomial. This is just the map that sends T eta Z to the product of Zi to the Xi. And so that map induces a homeomorphism from the quotient, from the symplectic quotient to C. We're going to say that P has degree n, which is just the sum of the Xi. So it's sort of the natural definition of a degree of a polynomial. So notice that we're calling this a polynomial, even though it's on our model Y, which is not a vector space. And in general, we'll treat things, if they're polynomials, if we have a T invariant function, which is a polynomial when we restrict to H naught cross CH plus 1, we'll just treat it as a polynomial. If this bothers you at all, just think about the case where H is equal to T, in which we have an honest to God polynomial. That's in any case the most important example. And I am claiming that this, so if you think about this, you know very well that if we're at a regular value and we have an n-1 dimensional torus on a 2n dimensional manifold, our reduced space will be 2-dimensional. So at regular values, it's more or less obvious that it's obvious that you get at least an orbifold at regular values, which will be 2-dimensional orbifold, so it will have to be homeomorphic to Y mod T. But in fact, I'm claiming this is always true, even at singular values, which is also not super hard to prove. But let's look at some examples. So suppose that Y is equal to C2. And you let lambda xy, let it act on the first coordinate with weight p, and on the second coordinate with weight minus q for pq greater than 0. So if you do this, it will be tall. So the reduced space at 0 will contain more than one orbit. If p and q were both positive, that would not be true. I'm sorry, if you're doing lambda p and lambda q, where p and q are both positive, that would not work. Then the moment map is very easy to check, that phi of xy is p times the norm of x squared minus q times the norm of y squared. And then the invariant polynomial is x to the q times y to the p. And you can check that this polynomial is invariant. And it's not hard, so that's just very easy to see, right? Because if we act, we're going to pick up a lambda to the PQ from the first term and a lambda to the minus PQ from the second term. And so it's sort of transparent that it's invariant. And it's not transparent that this gives you a homeomorphism, but it's true, and it is not terribly difficult. You know, it's like a third of a page proof. It's not a hard proof. So that's one example. Another important example is, say, y equals C3. And let's say our action takes alpha comma beta times xyz is alpha beta x, alpha inverse y, and beta inverse z. So here our maps are, our weights are 1, 1, -1, 0, and 0, -1. So in this case, our moment map is norm x squared minus norm y squared, and norm x squared minus norm z squared. And the defining polynomial is x times y times z. So again, it's very easy to check that this is invariant. The first, the x is giving you an alpha beta, the y is giving you an alpha inverse, the z is giving you a beta inverse. When you multiply those three, you're going to get 1. And again, you can check that it's a homeomorphism. And the final example I want to pick is a little bit different because it's an example with disconnected stabilizers. If you let y be equal to S1 cross over Z2R cross C, so this would be a point with Z2 stabilizer. And then S1 is just going to act on the first coordinate. And here Z2 acts on C by setting Z to minus Z. Then your moment map just sends lambda eta z to eta, and your defining polynomial is lambda eta z goes to z squared. And again, if you're acting on C by z goes to minus z, then clearly z squared is invariant under that action. Okay, so those are some examples of defining polynomials. Again, any questions for that? Okay, so oops, there we go. So now we're going to talk about what does it mean for a critical point to be ephemeral. And this is the most important new notion in this talk. So let G from Y to R be some T invariant function, and let P be the point 1, 0, 0 in Y. So given any L greater than or equal to 0, we can let T sup L of G be the degree L Taylor polynomial of G at P. So again, this is a little bit cheating. If we're on a vector space, we can just take the honest to God Taylor polynomial. If we're not on a vector space, we have to take the Taylor polynomial on the slice and then sweep the Taylor polynomial around using the action. But I'm still going to call this the Taylor polynomial. So we sort of treat Y as if it were a vector space. And it's actually very easy to check that that's fine. It doesn't cause any problems. So because we have an invariant function from Y to R, we of course can get a reduced function from the reduced space to R. Sorry, that should be a math blackboard bold R. Right, you just restrict and then take the quotient. Okay, so we have to say, what does it mean for a point P and Y to be an ephemeral critical point of G? Well, first of all, we need n greater than 1. So this defining polynomial, we need the degree of this defining polynomial to be greater than 1. And you see in all these cases, the degree is greater than 1. The only case, if you're over the interior of a polytope, for instance, the only time you will get n equals 1 is if you are at a free point. And in general, you will only get it if you have the generic stabilizer for that, the preimage of that facet. So these are what Yael and I call the exceptional orbits, if you're familiar with that notation. Right, so anyway, we only allow n greater than 1. So we're going to have some sort of non-trivial stabilizer, that's the point there. And we need that the Taylor polynomial of degree n minus 1 restricts to the 0 function on our reduced space. And we need that the 0 set of the n degree polynomial is homeomorphic to R. So what we have here is a map on the reduced space, which is equal to R2. So we want to map from R2 to R, whose kernel is homeomorphic to R. So an example of this would be, of course, if you have the map from R2 to R, but sends XY to X, its kernel is homeomorphic to R, and it's a regular. And so somehow what we're saying is we want these to look like regular functions on the reduced space. That's what this definition is meant to insist on. And so here are some examples. So let's say y is C2, and our moment map is sends xy to norm x squared minus norm y squared. Then we can, if we define g of xy to be the imaginary part of xy, then we will get the kernel is equal to R. And one way to see this, remember, is we've already said that in this case, our defining polynomial is xy. We're saying that the defining polynomial gives you a homeomorphism from the reduced space to C. So if you just take the imaginary part of the defining polynomial, it will always satisfy this. And the defining polynomial has degree n, so the n minus 1 term automatically vanishes. So therefore, it's clear that this is an example of that based on our theorem on the previous page. And the other thing is that this first example should be familiar. I'm sorry, it's kind of this should be familiar because this is exactly what our definition of a focus-focus singularity was. So this should be a familiar example. The next example is sort of just a generalization of this example, that we have, we let phi of xy be p of norm x squared minus q times norm y squared. So this will be weight p minus q. And in this case, we've already seen the defining polynomial is x to the q, y to the p. So again, we take the imaginary part of the defining polynomial. And our third example, similarly, we take the moment map on C3 that we saw last time, and we take the imaginary part of our defining polynomial, and we can also do that when we stabilize her with Z2. We just look and we take the imaginary part of our defining polynomial. The one thing I do want to point out is that these examples, the first one was the focus-focus. The second one is also one which has been studied in physics. This is called fractional resonance. It's something that people have been interested in. And the third one has come up in mirror symmetry. So yeah, these are not totally new examples. These are examples which have appeared in other contexts, and now we can take care of them here. And of course, the fourth example also is something we've seen. This is going to be hyperbolic type. This is an example of hyperbolic type, regular cross hyperbolic type. If you go back to our first. So these are all examples of ephemeral critical points. Are there questions again? Good place to see if anybody has any questions. Okay, so what are we doing with them? So a completely integrable system is...
Sorry, can I ask you to go back just to the slide? I want to finish processing the examples.
Yeah, sure.
Okay, so can you say something about the last one?
Yes, what?
I'm trying to get a picture in my head, and I'm having trouble with the,
Yeah, so, okay, so for the last one, if you want to understand it, what I suggest is instead of thinking about this example, think about just allow orbifolds. And just think about C with the Z squared action, with the Z2 action on it. I mean, otherwise you're just sweeping this out. So, fine, that's just, doesn't really contain any new information. And so if you look at C, you can look at the imaginary part of Z squared, right? So this is like norm, if you write it as X plus IY, this is sort of just X times Y. Or if you prefer, you can think of X squared minus Y squared. It doesn't really matter. But I might go with X squared minus Y squared because it's, right? So this is going to be a Morse function. This is a critical point. It's a Morse function, but it's index 1, right? So if you look at it, you're going to have like 2 regions where the function's positive and 2 regions where the function's negative, right? So
okay.
X plus, plus, minus, minus. So now what you're going to do is you're going to let Z2 act, and you're going to quotient by Z2.
I see.
And so now this X you had, which is 0, is going to become a single line of zeros. And your 2 regions where it's positive is going to become 1 region where it's positive. And your 2 regions where it's negative is going to become 1 region where it's negative. And basically what I'm saying is if you look at this, if you look at the map Z goes to Z squared, which gives you a homeomorphism from C divided by Z2 to C, then your function that was the imaginary part of Z squared just becomes just like the imaginary part of W. It's just which is sort of the natural regular function on C. Does that make sense?
And you said this appears naturally somewhere, and I didn't catch that.
Oh, this, yes. So this, the imaginary part of Z squared, if you go back, sorry, I'm having a little bit struggling with my page turning here, obviously. There we go. If you go back, you see this was the hyperbolic case. So there, this imaginary part of Z squared, and then our other function, our moment map, was just going to eta, and that was regular.
Okay, thank you.
It's the product of those 2. So yeah, that example, I'm not sure was natural or not. I mean, it's not, these are things that come up in physics, the hyperbolic points, of course, but yeah. Yeah, other questions about this slide? So, but that was actually a great question, because that really is, I think, the key idea of what it means to be an ephemeral critical point, which we started out with a point that was critical. I mean, the imaginary part of Z squared, that absolutely is, that's a critical point of your function. But when you go to the quotient, it becomes just the imaginary part of W, and there it's no longer critical. That's sort of the idea, is to take critical points and make them be regular points. And that's why it's called ephemeral. So people whose background is in some Latin-based language, ephemeral means something that does not live very long, very short, just disappears. And that's what's happening here. So
I wanted to ask one more question about that slide. Yeah, about the third example, you were saying that it has to do with mirror symmetry, and it looks sort of like the mirror to a pair of pants, but not quite. I wonder if you could say a little bit about that.
So no, I didn't write down the word mirror symmetry because I'm not really prepared to answer questions. So sorry, this is something I've been told, but I'm not gonna.
Okay.
Yeah, I think I don't dare get too far in. Okay, so right, so now we need to define near toric. So a completely integrable system, M omega F. Now I want to break it into phi G, where phi is n-1 and G is just 1 dimensional. And we're going to say is near toric if phi is the moment map of a complexity 1 torus action, and every point either has toric type or is an ephemeral critical point of G. So I allow either. And in fact, I didn't write it here because I don't know, I thought it might be more confusing, but I don't need every point to do it. I really only need every point that has a tall model. So it's okay if you don't need this to be true for all points, but sort of really even enough if it points over the interior have it, that's enough. You don't really care about the boundary. So an example is that every semitoric system is near toric. And this hopefully is fairly clear because near toric had to be either toric type or focus focus. And focus focus was one of our examples, the first example of our ephemeral critical points. So if every focus focus point is ephemeral, then clearly if all your points have toric type or are focus focus, then they all have toric type or are ephemeral. So that's one of the examples. And our main theorem is that if you have a completely integrable system which is compact and near toric, then all the fibers are connected. Oh, I said F, eta, and T star, but you could do Rn minus 1. And T star is Rn minus 1, so that's all good. Okay. I don't know if there's any questions there. What I would do is I will give the proof. So I don't usually give the proof, but this is actually one where you can actually give a pretty honest proof on a slide. In fact, I can give proof 4 things on one slide. So I'm going to look at, so again, I'm trying to prove that the fiber over eta and C is connected. So without loss of generality, I can assume that the reduced space over eta contains more than one point. Because if it only contains one point, then it's obvious that my fiber is connected, right? There's really not too much to say. So great. So it's a surface because, because it's going to be either 0-dimensional or 2-dimensional, and it's a closed oriented surface. And we're going to get an induced function G bar from sigma to R. So I'm calling the reduced space sigma. So this is the main sort of the details of the proof, which I'm obviously not including entirely, but sigma does not have a natural smooth structure, right? In general, we're going to be, if we're not over, if the action is not free, we're going to mess up the smooth structure, and the natural set of functions on sigma will not be smooth. But the claim is I can find a smooth structure on sigma so that this G bar is a Morse function. And the ephemeral critical points become regular points of G bar. So we saw that with the example of Z2 acting on C, that our function that was critical becomes regular. And more generally, this is the same thing, right? Our quotient looks like C, and we have some function whose kernel is R. So it's plausible and true that we can find a smooth structure so that it's diffeomorphic to a regular function on R2. And when we do this, points of toric type have a couple of options. A lot of points of toric type become regular points. That's sort of the generic thing to happen. But sometimes they become critical points of index 0 or 2, but never of index 1. So then we get a function G bar that has no points of index 1. And this is something that T and Gilliman proved, but it's sort of pretty obvious in the 2-dimensional case. If you have a Morse function with no points of index 0 or 2, then all the fibers are connected. So once you know that all the fibers in G bar are connected, in particular G bar inverse of C is connected, so then I can look at F inverse of eta C, and that's just phi inverse of eta intersect G inverse of C. So this is basically just going to be, if I take a quotient of this by a circle action, I'm going to get G bar inverse of C. So since that was connected, this is also connected. So this is a proof of the main theorem. And of course, the thing I didn't prove in this is how do I get the smooth structure? Why do ephemeral critical points become regular points? And why do points of toric type become regular points or critical points of index 0 or 2. All those things are anyway, you can prove them. That's sort of the main step in our proof. But yeah, those are all true. So any questions about the main proof? This is maybe the, okay. So I then want to talk about, at the same time, I can give you proofs of a number of other things. I can also prove that M hat is not toric. I can also prove that M tilde is not semitoric. And I can prove that the reduced space is a two-sphere. In principle, at some surface genus G, but I'm claiming it's got genus 0. So let me just talk about that. So we want to choose eta now in the interior of the moment image. So I now have a circle acting. So in those examples, I had a circle act. For the last thing, it doesn't matter. But let's say we have a circle acting. So if I have a fixed point of focus type, it must have weights +1 and -1 for the circle action. So it's sort of maybe not hard to see from the local model, but it's true. And also, fixed points of toric type must become critical points of G bar. So these are some more things that you can prove. So I said that points of toric type could become regular points, but if you're over the interior of your polytope and it's a fixed point, then it must become a critical point. It can't become a regular point. So then we're going to say, hey, well, since G bar has no points of index 1, then the reduced space must be a two-sphere. So again, if you have a two-dimensional oriented surface and you have a Morse function on it with no points of index 1, it had to be a two-sphere. But also, it can only have two critical points. So it's got a unique minimum and a unique local minimum and a unique local maximum. So it can only have critical points. And what we notice is if it's toric, then every fixed point must be a critical point. And it can only have two critical points. So we go back to our picture. Okay. Sorry. Okay. So now we see here, we have 3 fixed points. And I'm asking if it's toric. So if I'm asking it to be toric, then I'm saying every fixed point must be a critical point, but every moment fiber can have at most 2 critical points. So this is impossible because we have 3 fixed points, which would be 3 critical points. So this is ruled out. However, it's not ruled out for semitoric, because for semitoric, I allowed focus type. And focus could have weights +1 and -1. So this doesn't prove it is semitoric. I'm just saying that I can't rule out it being semitoric using this, because semitoric, you should have allowed to have as many fixed points as you want, as long as they have weights +1 and -1 and nothing else. So that goes to our next example, where we see here, it can't be semitoric, because if you look at this level set, there's 3 fixed points, and they have weights +1 or +2 and -1. So that's not plus and -1. So we're not allowed to have arbitrary number of them. We can have at most 2, but in this example, we have 3. So therefore, that's not semitoric. But it doesn't rule out it being near toric, because in near toric, we could have any weights we wanted, and it's still, we could have an ephemeral critical point. And so we could still get those, sort of sneak them in at regular values. And that's really the reason why ephemeral allows us to have a bigger scope, why near toric is a bigger example. Are there any questions on this? This is, I think, sort of a key step to understanding. Okay. So anyway, those are the main things for proofs. And then,
so could I ask an unrelated question?
Sure, absolutely.
So from the proof, your empirical singularity, when you define it, there is a power, there is a degree of the polynomial. So does it enter here?
So it does, but in the definition of ephemeral. So if you look back at the definition of ephemeral, so essentially ephemeral is meant, another way of thinking of ephemeral is it's a lot like the definition of Morse. Sort of you want something which is maximally non-degenerate, but the first time it's 0. So you see in the definition of ephemeral, you need, so the degree, you need the function to vanish below the degree, and you need it to be, and the one where you need to be coming over to R is on the degree of n. Essentially what you're doing is you're essentially forcing your last function to be the imaginary part of your defining polynomial in some sense. I mean, it's an infinitesimal condition. Well, Taylor series condition anyway, but it's basically, so that's where the degree comes in. Does that make sense?
So I was imagining that this degree would say something about the nature of the singularity that you have. But it doesn't seem to enter the proof at all.
No. The only place it really enters the proof, so really this n is telling you more about what's going on for the complexity 1 action. I mean, it really only is talking about what's going on for the complexity 1 action. And so this proof is we're already reducing by that and just looking at the reduced space. So we've already taken the quotient by that action in some case, in some sense. So in that sense, you wouldn't really expect it to come on. We've already gotten rid of that when we went down to the surface. And I think morally, that's the right way of thinking, is we're just looking at a function on that surface. Does that answer your question a little bit?
Yeah, maybe, yeah, and maybe have a weight impression. Yeah.
Okay, fair enough. I just want to talk a little bit, I guess I'm running out of time, that's fine. That additional claims, so I'm not going to define my terms in this, but if you've seen these, so Semitoric systems are really just for circle actions on 4 manifolds, so they're 4-dimensional, but you can do higher dimensions. So let M omega F be an integrable system, so that phi is the moment map of a complexity 1 torus action, and every critical point of F is non-degenerate with no hyperbolic blocks. So this goes back to what I was saying, so the formal definition of non-degenerate. Then M omega F is near toric in our sense. So we include these examples if you're interested in these examples. And these were already studied by Washu. So this is sort of the higher, this is one higher dimensional way of dealing with semitoric. And ours includes that, but definitely includes things which are not included in this. Another claim is our definition of ephemeral looks a little weird. Okay, I'm sorry, there's some hack in this, but there's a coordinate-free definition of ephemeral using jets. So you can define this in terms of jets, which makes it easier to check. So this is something you don't actually need to find the symplectomorphism. That would be quite painful. It's a pretty doable thing. It's basically like checking that something is Morse. I mean, if you understand it well, it's pretty doable, but as long as you can compute sort of the Taylor series, you're in good shape. It's a bit more work, but I'm sorry, I should say it doesn't depend on the choice of coordinates. But I think that's more complicated, so I just gave away Taylor series. Another point is that our main theorem holds whenever phi is proper. We don't really need compactness, but we do need phi to be proper. And then there's some questions. So is every 4-dimensional compact complexity 1 space M omega phi with the symplectic quotient S2, are they all nearly toric? So we proved that we needed the symplectic quotient to be S2. So you can ask, and we believe the answer is yes, though we haven't proven it. It's really a question. Certainly you can't prove it doesn't work. It seems to be that that means it will work. And I wanted to point out that Palmer and Hollock have a sort of a different extension of Semitoric, which allows sort of a different kind of degeneracies, but does not give you connected fibers, which is one thing that's nice about ours. But they can get off the 4-dimensional complexity 1 spaces. And I'll also just point out that if you allow other reduced spaces, you can never get connected fibers. That's impossible. So you can't possibly have both at once. And you can also ask what happens in higher dimensions. We're thinking about that a little bit. You will need to add more restrictions or allow more kinds of singularities. And the other question is like sort of, can we extend the classification of semitoric systems to near-toric systems? Anyway, that would be a nice thing to do. We have connectedness of fibers, which is a good first step, but of course there's a lot more to do. So anyway, so I think that's really the end. So I can take questions, but yeah, I'm done.
Okay, let's give Sue a hand. All right, any questions for Sue? Maybe I'll start with one. And I think you might have just answered this one, but I missed it. In the first question, is the reverse direction true, or how far away is it from being true?
So
yeah.
The question about the 4-dimensional case?
Yeah.
Right. So, right. So if you look here, so we prove that if it is near toric, then the reduced space must be a 2-sphere, right? So we usually say the complexity 1 space has genus 0. So something that's easy to prove is whenever you have a complexity 1 action, all the reduced space, all the reduced surfaces have the same genus. That's sort of, if you think about it, it's more or less clear, but anyway, it's proved. And so, and also, if you want to have connected fibers, you must have your reduced spaces be spheres, because you can't find a function on a surface that's not a sphere that has connected fibers if you want it to be like generically regular. It's just not possible, right? But we believe, so we know that it has to have reduced space 2-sphere, and we believe the converse is true. So we believe that all the ones with reduced space 2-sphere will be near toric, but I am definitely not claiming it, right? Like, yeah. So if you can go through and think about all these obstructions, and none of them prevent it. Like there's nothing preventing it from being true, but that, right, is a far way from saying I've constructed an example, right? So, yeah. Did that answer your question?
Yeah, it did. Thank you. Okay. Any more questions for Sue?
Yeah, I have a question, actually.
Yeah.
So in all of your examples of the ephemeral points, you had that G was the imaginary part of exactly the defining polynomial. Is that like what's going to happen all the time, or you can always arrange it to look like that or something?
So in this, it's like Morse functions. So it is not true that every Morse function on R2 is either equal to x squared plus y squared, x squared minus y squared, or minus x squared minus y squared, right? That's not true. But what is true is they behave as if they were, right? And the way Morse proved that they behave as if they were is actually show that that is the only local model, right? So we don't quite do that, but essentially, so there are other examples, but the other examples are all going to be, I mean, you can also do sort of stupid things. right, like I could add on, like let's say I would take the imaginary part of xy plus norm of x squared minus norm of y squared. I mean, so I can do other things which aren't interesting in some sense.
Right.
Or I could add, yeah, I can do, as long as I add small perturbations, it's fine, but they're not sort of, so these are the interesting ones in some sense. And everything else is just a perturbation from it in a way that won't matter. And really, we don't quite, like I said, get the local model, but what we do is we construct a homeomorphism of the quotients, which takes one function to the other, and is a diffeomorphism on the complement of 0, basically. So it's almost like a local model, but it's not quite, it's not quite the way we do it. So that's what I would, right? And the thing, Morse functions are the same, and that you could have like 2x squared minus y squared, right? But yeah, whatever. It's so really, I think Morse functions are a very good analogy to think like that. Like I said, though, we cut a little closer to just proving what we needed than Morse did. Yeah.
Thanks. That makes sense.
Other questions?
Okay, then let's give Sue one more round of applause.